So up until this point, every function that you've had has been defined in two variables. They weren't always x and y. Sometimes they were time or w or p or whatever, but everything's just been two variables. So we're going to talk in chapter 10 about parametric functions, which you last saw in Ham. And I don't even really know how much you saw it, because that, again, was, Ham would have been sophomore year. And I don't know if you were in person or if you were remote hybrid or what you did, but that was the last time you saw parametrics. We'll talk about vectors, and we're also going to do polar functions. So polar functions are the ones that make the really pretty graphs. They have roses and lemniscates and lemmacones and all kinds of stuff like that. So we're going to talk about the calculus of those things over the course of this chapter. So we'll start with parametrics today. Yeah, don't need that. Okay. So we're going to talk about the difference between what it means to be parametric versus Cartesian. Cartesian is what you have been doing. Maybe you didn't know that was the name, but that's what it's called, and how to take the first and second derivatives of those. All right, so let's compare and contrast what you have done. You have done what is called Cartesian curves. Cartesian curves are named after a French mathematician. And his name was Descartes. Let me spell it right. S, but you don't pronounce the S. So Descartes. He is the one who normalized the Cartesian plane, and the Cartesian plane is an XY plane. So he is the one who came up with that as a standard. He said, okay, we're just going to all agree that we're going to graph in the XY plane. We're going to plot points as X and Y. Came up with the grid system, where to put the first quadrant, where to put, who's going to decide where 1, 2, 3, and 4 go, what's going to be positive, what's going to be negative, etc. So he is Descartes. He came up with this, and everything that we've done so far has been on a two-dimensional Cartesian plane. So a Cartesian curve is a direct relationship between y and x, or any other two variables that you're going to plot on a two-variable grid. So that means one can be found using the other, a direct relationship. So if you know y, you can find x. If you know x, you should be able to find y. That's what a direct relationship is. Parametric is an indirect relationship, and it's between three different variables. It means you cannot find y or x unless you also know t. And t is a time variable. And so y and x are not related to each other in any way other than be related by the time that it's happening. And so this allows us, let me spell that right. This allows us to investigate, especially in a physics classroom or a physics sense, horizontal motion different from vertical motion, and how that would how those two things impact each other. So those are parametric curves. So you've got a third. It's not a variable. It's called a parameter. Okay, it's not a variable because in order to be a variable, what's the root word of that? It has to do what? It has to vary. And time doesn't vary. We don't control that. Time progresses. So time is a parameter, but not a variable. So the first thing we'll do is just stuff you did in Ham, converting from one to the other and looking at the time interval. Okay, so convert from this parametric equation where x is defined as the square root of t. So that means all the x values progress in a square root pattern. All the y values are progressing in a linear pattern. Okay, so you have a square root pattern versus a linear pattern. So they're progressing differently, found based on the interval of 0 to t. And then we'll sketch the curve. To convert from one to the other is pretty easy. We want to get y equal to something in terms of x. So do you remember how to do that from Ham? Okay, so they have t in common, and so we want to get t alone. And so if x is equal to rad t, then t alone would be equal to what? X squared. In other words, you're squaring both sides. And if t is equal to x squared, then we can take that and we can substitute it in for y, thus eliminating the parameter t. And so you'd have y equals x squared minus 2. So now you can tell that the overall equation is going to have the shape that's going to look like a parabola. So you took something that was a square root, who's a relationship of a square root, and something that was a linear, and it turned into a Cartesian parabola. Now they want us to sketch the curve, indicating the initial and terminal points, as well as the direction. So in order to sketch the curve, you want to make a table, and the time interval is controlled by 0 to 4. So what I usually do is I have a t, x, and y table all going on at the same time. And my time parameter is going to be 0, 1, 2, 3, and 4. So I should be able to find Cartesian coordinates from that. So if time is 0, okay, so I'll have each of you plan one. So Jonathan, will you be able to find the time 0 points, please? And Kaylin, find 1. We'll just have all the guys do it, okay? And then Christian, if you can find 2. Edson, if you can find 3. Alex, if you can find 4. All right? So using those time coordinates, you should be able to tell me the x and y coordinates, the time values. All right, so Jonathan, you ready?
0 and -2.
Okay, 0, -2. Now that is called the initial point. And the directions ask us to indicate what the initial point is. And so our initial point is 0, -2. So then on a graph, as we sketch the graph, we'll be starting at 0, -2, and you indicate what the initial point is, just using an arrow or something to indicate which one was the first point. Okay, Kaylin, you ready?
Rad 1.
Oh, come on, rad 1.
Square root of 1, -1.
What is square root of 1?
The x.
I know, but what is the square root of?
1.
Okay, let's just call it 1. All right, and then the other one?
-1.
Okay, so 1 and -1, so that would be our second point on here. Okay, Christian?
Rad 2 and 0.
Rad 2 and 0, so rad 2 is about 1.4. So we'll get as close to as we can to that. All right, Edson?
Rad 3, 1.
Okay, that's about 1.7. So about right there-ish. Okay, and then Alex, we'll end up at 2, 2. And that is called the terminal point, which is the final point. So we have terminal is that point. Okay, so the curve is going to connect those together. It wasn't the best. Let me see if I can try that again. It's a little better. And then the last thing, once you've labeled the initial and the terminal points, is you indicate the direction. And so that somebody looking at this would be able to know where you started and where you ended. So usually pick a different color and just kind of indicate which direction this curve is going. So we just took a parametric equation, converted it to Cartesian, it's going to be a parabola, and then created a graph. Okay, this is all ham stuff. Are we okay on that? Any questions so far? Okay, there are some famous parametric curves that you should know. And so as you should just be able to recognize them. Like, just like you know a parabola, just like you know a sine graph, just like you know any of these things, you should be able to recognize some of these famous ones. Okay, when you have x described as cosine, and when you have y described as sine in the interval, this is going to be, well, let's take a look at it, see what we get from the interval 0 to 2 pi. So we've got time, and we have x, and we have y. All right, and so I'll just go 0, I'll go to pi over 2, and pi, and we'll do 3 pi over 2, and then 2 pi, and we'll have our x and our y coordinates from that. All right, so Juliet, you'll take the first one, and then Rain the second one, and we'll loop back over. Jonathan, take the third one. You take pi, Kaylin 3 pi over 2, and Christian 2 pi. Okay. All right, so Juliet, are you ready? Okay.
It's 1, 0.
Mm-hmm. Okay. Rain?
0, 0.
It's not 0, 0. The cosine of pi over 2. Now, do you like to do it with unit circle in your brain, or are you thinking like the waves? How do you usually? You're doing unit circle?
1.
Okay, so the unit circle for pi over 2 is straight up on that. So the top of the unit circle. 1 for what?
For
Okay.
Sorry, I totally forgot everything. Not zero.
It is 0. Okay, but the other one's not 0. You said 0, 0.
Oh.
So,
And then sine of pi over 2, 1.
okay.
Sorry, I thought I said sine of x.
There we go. Sine of t. Sine of t. Sine of the time. Okay. Jonathan?
-1, 0.
-1, 0. Okay.
0, -1.
0, -1.
1, 0.
1, 0. So let's take a look at what that's going to end up looking like for us. So our initial point would be 0, 1, which is right here. Okay, our secondary point was, 1, 0, and then 0, 1. And then -1, 0. And then 0, -1. And then back to 1, 0 again. So the initial and the terminal are on the same section. All right, so then how do we connect that? Okay, is it connected like this? Okay, do you think that's how it goes?
Same like a circle.
It is, it's a circle, okay? Okay, we're not gonna be connecting it this way because sine and cosine don't make linear values. Sine and cosine make curved values. And so rather than, it's gonna be more of a unit circle. And what do you know that is graphed in this, that goes like that? Yeah, this is the unit circle. This is the graph of the unit circle. And sometimes I'll put my arrows on it like this to kind of show that I'm curving in a counterclockwise direction. So when you have x being equal to cosine of t and y being equal to sine of t, you get the unit circle. And the unit circle has radius 1. Okay, so let's see if we can make a decent guess as to what might happen in part B. In part B, we still have x being defined as a type of cosine and y being defined as sine as well, but it's not going to make a unit circle of radius 1. Anybody want to take a shot at it?
Turns into an oval.
An ellipse. Yep, an oval, okay? And so the reason why would be what would happen to the x coordinates. So the time coordinate, if we followed that, our time parameter, and then our x and our y. The y parameter is going to be exactly the same, 0, 1, 0, -1, 0. Our time parameter staying the same. But then our x coordinate, because it has the 3 as an amplitude, is going to be 3, 0, -3, 0, +3. And so it's stretching the figure. And so we're now going from 3, 0 being our initial, and then 1, and then -3, and then 1. And so what we're going to get is what we call an ellipse. Okay, and so then we'll put some arrows on there showing that we're traveling in a counterclockwise direction. And so this is an ellipse, and it doesn't have a radius anymore. But again, you learned your your conic sections in HAM. What an ellipse has, instead of having a radius, an ellipse has a major and minor axis. So it has a major axis and a minor axis. The major axis is, of course, the longer axis, and it's ±3. And the minor axis is ±1, which is what makes it an ellipse. The thing about a unit circle is that its major axis and minor axis are equal. And they're both equal to -1. That's what the definition of a unit circle is. But an ellipse has various. So how would you have to modify the original equation to get your ellipse to go the other direction?
Move the 3 to this side.
Okay, you'd have to impact the y. If you were going to impact the y coordinate, say by 5, then you're going to have an ellipse that's going to be more tall than it is wide. Its major axis would be ±5, or excuse me, its vertical axis would be much ±5. Its horizontal would be plus or minus 3. So you can manipulate any x equals cosine and y equals sine. You can generalize that, okay? So if you have y equals a cos x, excuse me, a sine x, sine t, preceded by x equals, let me see, nope, I want the a to be that one. X will have the a cos t, and b sine t, let's say like that. Any parametric equation set up in that format, where a is a constant number and b is a constant number, this will always produce something round. Well, let's call it elliptical. Okay? Because elliptical does cover a circle. A circle is an ellipse. A circle is just an ellipse that has equal major and minor axes. Okay, again, we haven't done calculus yet. This is all still ham review. Got that? Okay, any other questions so far? What would happen if I limited the time parameter? So what if I took this time parameter here, and instead of giving you 2 pi, I took off the 2 and said you were only allowed to go to pi? What would that look like? Okay, if you're only going 0 to pi, that means you're only including the top half. So you're going to go around and then stop. If you wanted to limit only the left half or the right half, if you wanted to control different quadrants, you could limit that as well. You could change the time parameter and say, I want you to go from pi halves to 3 pi halves. That's going to give you only what we call the left half of the unit circle. Okay, it's going to be quadrant 2 and quadrant 3. Okay, so you can control how much of the graph you're looking at by controlling the time parameter. If you can control time, you can control what you're looking at. Okay, so these are the parametric curves that we've seen so far. We have seen a parametric curve that turned out to be a parabola. We've seen a parametric curve that turned out to be a unit circle, and we've seen a parametric curve that turned out to be an ellipse, and you should be able to recognize those, okay? And so in general, this is going to happen when x is a square root and y is linear. If you reversed those, if you made the x linear and the y be a square root, you'd still get this sort of shape, but you're going to get one that's going to look like this instead. It's going to be a square root that's going the other direction, okay? More of a horizontally opening square root. And we've already talked about the elliptical one, generalizing that, where x is generalized to be a cos t, and y is generalized to be b sine t. Just like a unit circle, x is always the cosine coordinate, y is always the sine coordinate. All right, so now let's get to actual calculus and how the derivatives work. The derivatives are super easy. To get the first derivative, dy dx, you stack the y derivative on top of the x derivative. That's it. All right, so in other words, it's the y derivative in terms of t over the x derivative in terms of t. It's so easy. Do you remember anything else where we've stacked derivatives on top of each other? L'Hopital. Yep. And there's a connection between L'Hopital and parametric equations as well. The second derivative always catches people up, though. The second derivative is not just the second derivative of the top over the second derivative of the bottom. The second derivative is the second derivative of y in terms of but you leave the bottom one alone. Where else have you seen the phrase like, do something to the do something, but then leave this part alone? Does that ring a bell for anything we've done before? Okay, it's the chain rule. Okay, it's a chain rule. If you do take the derivative of the outside, but leave the inside alone. Okay, this is very much like that, and it's actually proved by the chain rule. We're not going to prove it today. But you take the second derivative of the y value, but you leave the first derivative of the x value alone. Okay, don't touch that at all. Yeah.
So with the third derivative?
Yes. Nope. Leave it.
Just leave it still?
Mm-hmm. Mm-hmm. All right, so let's practice that. All right, find the tangent line to the parametric curve. All right, we're really good at this. What do you need to find a tangent line? Point and slope, okay? To find the point, we're just gonna plug the values in to find our x and our y coordinates. So we're gonna do our point first. So our point would be x equals the secant of, and the time parameter we're given is the time of pi thirds. So the secant of pi thirds is the reciprocal of the cosine of pi thirds. So again, I don't know if you're a wave person, if you're thinking of the wave in your mind, or if you're a unit circle person and you're thinking of what that is, but this would be, the cosine of pi thirds is 1/2. So this is the reciprocal of 1/2, so 2. The y value would be the tangent of 2 times pi thirds. In other words, the tangent of 2/3 pi. So that'll be the sine of 2 pi thirds over the cosine of 2 pi thirds. So one of those has to be negative because we're in quadrant 2 this time. So again, this is be your personal preference. I envision a unit circle in my brain. That's how my brain is going. And so when I go to sine of 2 pi thirds, I put myself into the second quadrant, and I know that that is rad 3 over 2, and then the other one is negative 1/2, which would simplify to negative rad 3. So that gives me my point. And then I would need the slope, and the slope will come from dy dx. So dy dx is just as simple as the derivative of y. Okay, so let's take the derivative of y. What is that? Secant squared of 2t, and then what else? Times 2. Good. And then the derivative of the denominator, or the other one, of the x would be secant t tangent t. Now, I know we have a secant in the numerator and another secant in the denominator. Those don't reduce because one of them is of 2t and the other one is of regular t. So that's as far as we can go, but we can evaluate that now, the parameter pi thirds. So this would be the secant squared of 2 pi thirds times 2 over the secant of a single pi thirds times the tangent of pi thirds. And you'll just pull all these values off of your unit circle. So secant squared of 2 pi thirds would be 1 over the cosine squared of 2 pi thirds times 2 and then 1 over the cosine of regular pi thirds, and then sine pi thirds over cosine pi thirds. So again, all of this, I'm just being careful since it's our first day back. We're just trying to cover all of this. Normally I'll probably go through this a little bit faster. So I need to know what the cosine is at 2 pi thirds. The cosine at 2 pi thirds again puts me in quadrant 2, and that would be -1/2, but I'll be squaring it. So this would be 1 over -1/2 squared. And my denominator is 1 over +1/2. And then the sine is rad3 over 2, and then +1/2. So we have a lot of taking the reciprocals and things that we should be able to simplify here. So as I simplify that, what's the numerator going to come out to be? If I square that -1/2 and then take the reciprocal and then figure that out, it's going to be 4 times 2. Yeah, so it'll be 4 times 2, which is 8. And then my denominator, when I simplify that, it's 1 over 2, so that'll be 2 again. And then the square root of 3 over 2 over 1/2 will be the square root of 3. So you can see how this is going to simplify. 4 times 2 over 2 times rad3 to 4 over rad3. So this is just where your trig and your simplification might trip you up if you get stuck. So now we have all the parts we need. We have our point, which is 2 and -rad3, and we have our slope, which is 4 over rad3, so we can write our tangent line. So our tangent line will turn out to be y minus the square, plus the square root of 3 equals 4 over the square root of 3 times x minus 2. All right, how are we doing? Are we tracking okay? Okay? Yeah, all right. Okay, here's another application of using derivatives in pairs. So it's the same concepts we had before, we're just using a different structure because we're using different equations. So, is that warm air making you sleepy? Yeah, and right after lunch. Okay, I might have, oh yeah. You need a little mint? I always like that. Like in church, I always have a little mint, and that helps me stay awake.
Thank you.
Yeah, it was gorgeous.
Want one?
Yeah, we use, I think, 30.
Did I give you 2? Pass one over. You guys want one? Jonathan? All right, there's one, should be one extra coming over. Oh, all right. Yeah, there you go. All right. Okay. Find the points where any tangent line would be horizontal and or vertical. All right, so what's the definition of a horizontal line? How do we find that? What kind of derivative? For horizontal? Okay, the derivative should be equal to 0. And then what about vertical? 1 over 0. Good. Okay, so first our first job is to do what? Find the derivative. Okay, so let's find the derivative. And so our dy over dx will be the derivative of y. All right, Alex, you want to do the derivative of y for us? Good job. All right, so 3 cosine t. All right, Edson, you want to do the derivative of x for us?
Derivative of x would be 3 or -3 sine t.
Okay, so -3 sine t, which would just simplify to negative cosine of t over the sine of t. Now, it's kind of arbitrary where you put the negative sign. It could be either in the numerator or the denominator. Convention usually puts it in the numerator. I'm not going to simplify this to cotangent because I want there to be a numerator and I want there to be a denominator so that I could set it equal to 0 and 1 over 0. So it's not wrong to change it to cotangent, but then you're just going to have to change it back. All right? So to find our horizontal positions or moments, we'll take negative cos t over sine of t, and we'll set it equal to 0 technically over 1. And to find our vertical time moments, we'll take our derivative, our slope, and we'll set it equal to 1 over 0. And then the math just becomes cross multiply to solve each of those. So for horizontal, once we cross multiply, we'll have that the negative cosine of t equals 0. And that's going to happen multiple times. It's going to happen every time, every moment that our time is equal to pi over 2 would be the first one. And then it's going to happen again at 3 pi over 2. And it's going to happen at 5 pi over 2. And so to generalize that, it's going to happen at k pi over 2, where k is an odd number. So every time we come up to an odd value, we will have a horizontal tangent. For vertical tangents, again, we'll cross multiply, and that will give me the sine of t equals 0. And that happens multiple times as well. The first time it happens is at 0. Then it'll happen again at pi, and at 2 pi, and at 3 pi, etc. So we can generalize that to any k pi, oops, that's funny, for integers. Okay, k could be any integer. Now, does this answer the question? Does not answer the question. The question is, find all the points when this happens. So we have now found all the times when it happens, but we haven't actually found all the points that it's going to happen. So we actually have to finish this and to find horizontal points. Because I want you to think back to what we've talked about already. What is the shape of this going to be? Because x is described as a cosine and y is described as a sine. So what shape are we talking about here? Okay, circle. Now think about like the major and minor axes or whatever. So the x is going to be this way. So it starts out because of the 3 in cosine going from 3 to negative 3. And the y, the sine, talks about going from 3 to negative 3. But what the extra numbers do, what this does and this does, is move the center. Okay, so it's going to move the x center to negative 2. And it's going to move the y position to positive 1. So we're still looking at a circle, but the circle's just been moved off center a little bit. So the circle is now sitting at negative 1, 2 with a radius of 3. So if you can picture that, this is where we're at. We're at negative 2 for x, 1 for y, and then we're at a radius of 3 in all these directions. So we're looking at a circle that goes like this. Ooh, it's not the greatest. Okay. Well, where is this going to hit horizontal tangents? Okay. Well, not x, don't tell me x, but it's because we're talking in terms of time here. But every time we hit that, it'll be horizontal tangent. And then every time we hit this, and then because the parameter just keeps going around and around and around. And for vertical tangents, it's going to hit every time we hit here and every time we hit there. Okay, those positions. So this should be, if this is negative 2, this is a and this is 1, and the radius here is 3, then what should that point be? Should be negative 2, comma 4. And what should this point down here be besides being negative 2? -2. Yeah, it's 3 lower. We're dealing with a radius of 3. And we can confirm that by plugging the time values back into our parameter. We can do it by visually, or you can plug it back in. To finish up, as we want to look at the inflection points, we know that we need the second derivative. So we have the first derivative already from our work before. So the first derivative was negative cos t over sine t. And so to find the second derivative using the rules for parametrics, that we take the derivative of the numerator, but we leave the denominator alone. So that would give us the positive sine of t over the sine of t.